Hello everyone, this is our test video, though we have promised to start with quantum mechanics, but this is the first test video we are going to unload. And let it not scare you that we are going to use mathematics. When we come to quantum mechanics, we are going to explain it in ordinary language as much as we can. For now, this test video is for those who have a background enough to know classical mechanics, kinetic energy in classical mechanics, and what we call a relativistic factor, which is not which time would not allow us to prove here, but I intend this video for those who know what the relativistic factor is. What we are going to prove now is the mass-energy relation, which is actually very rare in physics textbooks. So we go, mass-energy relation. In classical mechanics, we know that kinetic energy is given by the integral of force over the distance from wherever you start. If you start from 0, let's say your starting point is 0, then integral from 0 to s. But we all know that F is equal to d dt into mv. So in essence, this integral is like saying the integral of d dt into mv ds from s to 0. We know that ds dt is equal to dv. So simply this integral is the integral of mv dv from 0 velocity to final velocity, which will give us mv square over 2 in from 0 to v, which is which is exactly equal to this one. When you evaluate this, you get half mv square, and every high school student knows that half mv square is the kinetic energy of an object. But relativistic mechanics comes with something else, that the speed of an object or the kinetic energy of an object adds to the total energy of the object, because mass and energy are one thing. Like mass can evaporate into energy and energy can condense into matter. Then the kinetic energy itself is an addition to the mass of the very object. So we all are aware of the relativistic factor 1 over 1 minus v square over c square, where c square is the speed of light and v square where c is the speed of light and v the velocity of the object. So you can see that as this approaches 0, this gives you 1. So as the speed of the object approaches 0, relativistic mechanics become approximated to classical mechanics. Henceforth, we will call this relativistic factor gamma. And let us go. The theory of relativity decided to take the matter in a different way. It says kinetic energy is equal to the integral of v dm v from 0 to v m naught, of course, because m naught in relativistic mechanics represents rest mass. So this one is a double function, and we can remember our good old rule of integration by part, whereby the integral of u dv is equal to uv minus integral of v du. Let me put it clear. The integral of u dv is equal to uv minus the integral of v du. So in relativistic mechanics, everything has to go with that relativistic factor that we now announce that henceforth we will call gamma. So this is a function, this is another function. So first we have integral of v dm v is equal to uv, which is a multiplication of this, which is m naught v square over gamma, the relativistic factor, because it will account for the increase of the mass of the rest mass m naught, because we are interested in kinetic energy when the body is in motion, minus the integral of v, which is m naught v dv from 0 to v. This seems to be very simple, but there is always the constant relativistic factor gamma, which we can put it this way, minus the integral of mv dv over gamma from 0 to v. So if you follow me, we have m naught v square over gamma minus m. This gamma can come out of the integral function. So m naught v or dv, which is equivalent to 1 over gamma into m naught v square from 0 to v, which will actually give us 1 over gamma into mv square over 2. So in a sense, kinetic energy becomes Ka is equal to m naught v over gamma minus m naught v over 2 gamma. So I think you can understand when we do something like this and say kinetic energy is equal to gamma mv minus m naught v. Gamma mv square minus mv square. In that case, so as our kinetic energy is equal to gamma m naught c, because in relativistic mechanics, which I call the physics of the very fast, we deal with speeds that approach the speed of light. So here we are going to use the speed of light, mc square. C replaces v square, c square replaces v square minus m naught v square. So m naught is the rest mass of the object. So the relativistic mass when the object is in high speed is relativistic mass is equal to gamma m naught is equal to m. Therefore, kinetic energy becomes, so this is the rest energy. So, and this is the total energy, including rest energy and the kinetic energy, which is contributed by this gamma. So, our kinetic energy becomes I'm a bit fast. Ke is equal to mv square minus m naught c square, which is the total energy of the object minus the rest energy of the object. From here, we have rest energy of the object. Object at rest has mass of the object. Energy contained in every object of mass m is the mass of the object at rest multiplied by the square of that of the speed of light. And when the object is moving, then the total energy of the object is E total is equal to gamma m naught c square, where gamma will change m naught to mc square. So